Yeah, it's my pleasure to introduce George Papas from the University of Toronto, and he'll be speaking about height bounds for certain exceptional points in some variations of Hodge structures.
Thank you again very much for the invitation. So I wanted to start with a little bit of background and mainly the motivation behind this work. First of all, so our motivation. So this is work of Andre. And as far as I know, it's essentially the work that started a lot of the modern version of unlikely intersections and the Andre-Oort conjecture and what followed after that. So we consider the following scenario. So S prime is some curve. So he considers the following scenario. So S prime is a curve, smooth connected. Over some number field K. And he considers also a point, a closed point on the curve. And he lets S be the complement, essentially, of that point. And he lets F from X to S be an abelian scheme. Defined over K, and H is the veil height or a veil height on S prime. And I will also let G be essentially the dimension of the fiber. So this thing. So this is the theorem of Andre that at least started this this question that I've been thinking about. So let F over X from X to S be as above, and we assume the following. We assume that it has a completely multiplicative reduction at S naught. Which essentially means that the neuron model of this abelian scheme over S naught will just be some GM to the G, the dimension. So we also assume the geometric generic fiber X at the bar is a simple abelian variety. Of odd dimension G. So he needs this dimension over here to be odd and bigger than 1. And in that case, Andre considered the following set. So he considered the set of points defined in, let's say, Q bar, such that the endomorphism algebra of the abelian variety given by the fiber over that point does not inject inside MGQ. And in that case, he actually proved that he can find two positive constants such that the height of the point S is bounded above by C1 times essentially this thing. So Ks, the degree of the extension to the C2. So, and this holds for all such points in this set.
So MG is moduli of genus G?
No, this is just G by G matrices
Ah,
of
okay.
MQ.
I was wondering how an endomorphism algebra fits into moduli.
Yeah, no, this is
Okay.
especially from Northcote's theorem, this would imply that there exist finitely many such points. With bounded degree. So with KSK bound. And as far as I know, and I might be extremely wrong, this theorem actually, I think, gave Andre the idea of stating the Andre part of the Andre Oort conjecture, at least in AG, as far as I know. Maybe it's for general similar varieties, but yeah. So yeah, that's the motivation that we started the work here. And the idea was, can we do something similar for variations of Hodge structures? Can we say something along these lines? But before I go into that direction, I wanted to say some things. So first of all, this condition over here. So this condition that the endomorphism algebra does not inject inside MCQ. It's actually a condition that says I have a lot of endomorphisms at the point. And it should be contrasted with the fact that just the endomorphism algebra generically will inject inside every such endomorphism algebra, and in particular, it will inject inside MGQ, which happens to just be the algebra of the fiber of the neuron model, of the connected neuron model, which would just be a GM to the G by this assumption that it has over here. Okay. Should work. Okay. Before I go on to my result, I wanted to talk about sort of why this is useful, and this result of Andre, this height bound over here, is useful in unlikely intersections. So here's a quick introduction to problems of unlikely intersections.
George, can I ask you a question about that statement? So the endomorphism algebra obviously would embed inside 2G by 2G matrices, in obvious way.
Oh, yep.
But then the reason you have here G by G matrices, and you're looking at that this has something to do with that multiplicative reduction condition?
Yeah. Yeah, I think it's, unless I remember extremely badly, I think it's just a property of the neuron model, right? So the generic algebra of endomorphism, so the endomorphism of the abelian scheme should be injecting inside every fiber, inside the endomorphism of any fiber, and in particular of the fiber of bad reduction, essentially, which just happens to be GM to the G, which is just MGQ. So it restricts a lot in a sense. So, and especially I think this, assume that the geometric generic fiber is a simple abelian variety, tells you that it has to be fairly small. Like generically, the algebra will be fairly small. It won't be like a CM field, is the point.
Yeah. Thanks.
Yep. Okay, so just the general idea of problems of unlikely intersections. So usually in unlikely intersections, one considers some ambient space that I'm going to call C. And then we look at closed irreducible subvarieties. So X and Y, some closed irreducible subvarieties. Everything for me, at least here, is happening over C. Then let's assume that the dimension of X is R, the dimension of Y is S, and the dimension of Z is N. And let us write X intersect Y as some sort of union of irreducible components. Then it's very natural to expect for just naive counting reasons. So natural to expect by a naive count that the dimension of each such component will actually be just R plus S minus N. And then the general problem of in unlikely intersections, so a general problem looks a little bit like this. So we fix X and let Y vary in some countable family that I'm going to denote by YZ of subvarieties that are usually called special subvarieties. So usually they carry some arithmetic property. Some examples of this is, for example, one could take Z to be some torus over C, in which case the special sets, the special subvarieties are just torsion cosets, which means they're of the form Z times G, where Z is some torsion point inside Gm to the n. And G is some closed irreducible. I don't think anything closed. It's automatic. Irreducible algebraic subgroup of Gm to the n. Another example is when Z is some abelian variety, again over C, in which case again YZ is torsion cosets. So things of the form P plus P, where P is some torsion point and B is some abelian subvariety. And in far greater generality or difficulty maybe, Z is some similar variety, and then YZ are the special subvarieties in similar varieties, which take quite a lot to find. And the idea then is to try to isolate when this isn't happening. So in general, the dimension is at least this much. We expect that it's always equal when it's not happening. So when it's bigger, we think that should be atypical. So one defines when this is the torus or some abelian variety or some similar variety. And X subvariety. One says that an irreducible component A of x intersect y for y inside the special for y being a special subvariety, A is called atypical. Subvariety of x if the dimension of A is bigger than the dimension of x plus the dimension of y minus the dimension of z. And one also lets at x be the union overall y in yc of atypical subvarieties of z, of x, sorry. So a priori, just from the definition, we get, because these sets YZ are countable, that this union has to be a countable union of subvarieties of X. The Silberping conjecture, so Silberping conjecture predicts that in fact this union is finite. So for X and Z as above, the atyp X is actually a finite union, or in other words, there exists finitely many maximal atypical subvarieties. And there, sorry, and as a conjecture, it's fairly open, but there are some results out there, some conditional, some unconditional, and some partial. So in the case where X is a curve and Z is some torus, the Silberping conjecture is known. And this is by work of Bombieri, Habeger, Masser, Zanier, and I think Morin as well. When X is a curve and Z is Y1 to the N, Silberping is known conditionally on what is called the large Galois orbits hypothesis, and this is work of Habeger Pila, and unconditionally under the assumption that X is what they call asymmetric. And this is also Habeger. And this asymmetricity condition is something that they need in order to establish this large Okawa orbit hypothesis, essentially. And finally, so for a curve inside AG, there are some partial results. And for G equal to 2, silver pink is again conditionally known. Assuming some large scale orbit hypothesis again. And this is work of Do and Or, and some partial unconditional results of Do and Or again. Exist, and they make extensive use of this height bound of André. So here's what a theorem would look like in A2. So this is Do and Or. So X inside A2 is some irreducible Hodge generic curve. Defined over Q bar such that there's a risky closure of X inside the Bailey-Borel compactification of A2 intersects the zero-dimensional stratum of the boundary of the Bailey-Borel compactification. Then the set X intersects sigma is finite, which is what the what the Silberling conjecture boils down to in this case, where sigma is the set of that contains, it's the set of points in A2, parametrizing so CM abelian surfaces, what they call E cross CM abelian surfaces. So surfaces that look like E1 cross E2, or E1 and E2 are two elliptic curves, and E1 is a non-CM elliptic curve, and E2 is a CM elliptic curve. And finally, abelian surfaces with quaternionic multiplication. Okay, and this condition that the Zariski closure of the curve inside the Bailey-Borel compactification intersect the zero-dimensional stratum is essentially the condition of André that this the abelian scheme that he has over this curve S. So he has that. Okay, let me change notation a little bit here. So we have an abelian scheme over the curve X. This abelian scheme will have over S naught, but it will have multiplicative reduction. Essentially, is that condition about the zero-dimensional stratum. And they need the height bound of Andre to establish this. Here, a missing part, and the only missing part in this case. So the only missing part to establish the silver ring conjecture in this case is to check that in such a scenario, the points that the intersection of the curve X with the points that describe parameterized, abelian surfaces that are isogenous to some square of an elliptic curve is finite. Okay, that's it from that. So that's a little bit of the motivation behind the work that I've been doing. And the second part is actually talking about that work. So how do we pass from abelian schemes to variations of Hodge structures? And the idea is that this height bound is essentially a theorem about periods. So the idea was, can we translate to general periods, essentially? And that's what I'll try to explain now. So given some smooth projective morphism, we have okay, over some number field as usual. So over everything is defined over some number field. We have the relative version of growth index comparison isomorphism. Which we can write as H and the RAM X over S with the sheaf of analytic functions is isomorphic to this local system tensor again over Q with sheaf of analytic functions. So this is algebraic the RAM, and this is essentially basic homology. Oh, sorry. In particular, so the right-hand side of this is a polarizable variation of Q Hodge structures of weight N. And this ends working. And the idea was that when we look at this isomorphism over here, when X is some abelian scheme, and N is 1, we recover generic algebra of endomorphism of X and the algebras of endomorphisms of the fibers as the algebras of Hodge endomorphisms. And I'll hopefully have time to explain what that is later. Hodge endomorphisms of either the variation, when we're talking about the genetic algebra of endomorphism of the scheme, of the abelian scheme. So the variation R1 F analytic goes forward like that, or respectively the algebra of Hodge endomorphisms of the Q Hodge structure H1 XS amplification. So the general idea is, can we keep on translating the ideas behind what Andre does to higher weight variations of constructions? So the question that we tried to answer was, can we establish analogs of Andre's height bounds for variations of code structures of arbitrary weight? And the answer is yes, sometimes. So conditionally, we can. Okay, so I'll start with a little bit of notation. So my setting is just slightly different. So S prime for me, sorry, first of all, K is some number field. S prime is some smooth proper geometrically reducible curve over my number field. Sigma S is some subset, finite subset of points on my curve, and we select a particular one of them. So certain point in S prime, and we also set S to be the complement of sigma S on S prime. We will also consider just as above. So F from X to S is some smooth projective morphism defined over my number field K with n dimensional fibers. And my assumptions will be that I can find a smooth K scheme X prime and the projective morphism. Extending, extending X over S prime. So I will have such that, first of all, this is happening. We have this commutative diagram. So this commutes. Prime. And my second assumption is that Y, the fiber of F prime over S naught, is what is called a simple normal crossings divisor. Which essentially means that Y is union, turns out, of n plus 1. Transversally crossing smooth divisors entering the fiber with multiplicity 1. So essentially, we're assuming that over some particular point that we have chosen a priori, that we have some very aggressive degeneration of this geometric family. And I want to quantify this aggressiveness in a certain sense by considering the following situation. So I'm going to take some small function, small disk, analytic disk, centered at S naught. With the puncture disk contained in S. And in this case, we have monodromy acting, get monodromy acting on what we're interested in fact, here is the following SIF. So local system over Q, and I actually want to do all of this. And think that, at least I think about this as just the sieve whose fibers are, are nothing more than homology. And in this case, we get the monodromy acting on this. We let be the logarithm of the monodromy, which in this case would be, because of this condition over here, the monodromy would be unipotent, so I can actually consider the logarithm. And the logarithm would be a nilpotent endomorphism. And there's this whole business of a weight filtration known from the Lin, as far as I know. And in this case, I will define the dimension H to be the dimension of the image of n to the n. Let's see, for n. C star. And essentially this coincides with the weight zero part of the weight filtration. Of the limit mixed Hodge structure, for those who know. Okay, and under all of these assumptions, I can actually state my result. So we let K the number field, F from X to S, the projective morphism, X prime over S prime B as above, S naught, H, and we assume the dimension of the fibers N is odd, that the Hodge conjecture holds. And what we refer to as good arithmetic models, or one of them, so a good arithmetic model. Exists for the morphism F, I don't want to good arithmetic. Yep, didn't mess anything up. So, yep. So we consider the variation to Hodge structures given by the local system defined as such, and we assume that the generic special Mumford-Tate group of this variation, which I could denote like that, is just the symplectic group where mu will be the dimension of let me stop this. Okay, and in this case, we can consider the set again of points defined over Q bar, where the endomorphism, so the algebra of endomorphisms of Hodge structures of the fiber is large, and I'll try to make some remarks on this largeness later. And then we get the same result, that we can find positive constants such that the veil height of the point S is bounded by KSK C2 for all points in this set. Okay. Okay, and some remarks about this largeness. So first of all, this set will contain all CM points of the variation, show contain. And some actual examples of what these points should look like. So for example, when the dimension is 16, and if we assume that this number over here, h, is 4, then we can actually construct infinitely many examples where of algebras that look a little bit like this, where F is a CM field over some totally real field F naught. And the endomorphism algebra is some quaternion algebra over F. Then any point that has these properties will be in this set S. I don't have particularly clean conditions. I think the cleanest I could actually prove was something that looks like the following. So VS is a simple polarized Hodge structure. And its endomorphism algebra satisfies the following. Its center is large. How large? Larger than certain quantities coming from just a variation of Hodge structures. And again, we also need some largeness compared to information essentially coming from the degeneration at the point S naught. So something that looks like this. And okay, and I could go over a little bit of the strategy about how one could go about proving examples, results like that. And the idea is that once we have this X over S, where S, where S is this curve minus this finite set, and S naught is as above. The general idea is sorry, give me a moment to phrase this better. So I also need a local parameter of S prime at S naught. And the idea is that this isomorphism of Grothendieck if everything is coming from, sorry, if everything is defined over a number field, as is in our case, then a particular, sorry, let me phrase this better. We can write this as locally as a matrix sorry. And I'll explain all of my notation. Where the entries in the first 8 columns are G functions. And the idea then is that at points S, let's say defined over some number field L, such that ds is particularly large, if we were to look at places that are Archimedean, the largeness of ds together with the absolute Hodge conjecture would give us algebraic relations among the values of these particular periods at the point S. And then, sorry.
George, I think you said this, but just to clarify, DS is just endomorphism algebra, the Hodge structure, or what was DS?
DS, yes.
Yeah.
Apologies, I forgot to define this. Yep. So for me, DS is just the endomorphism algebra of Q Hodge structures at the fiber. Sorry. And at the point, sorry, and that over the places, over the rest of the places, the finite places, again, our largeness conditions are such that we can assume that S is far away from S naught. So S is not close to S naught. Viadically. And if you put those two results together, the end result is something that says something along the lines of the relations created here are sort of non-typical. They shouldn't exist unless the point is very, very simple. Or in other words, one uses what Andre refers to as the Hasse principle for the values of G functions to arrive at a height. Yeah, that's it. That's all I had to say. I think I beefed it a little bit at the end. Sorry about that.
Thanks a lot. Very nice talk.
Thank you.